What is your? Yeah. What you want? What you do? You and Siddles. Yeah.
Okay. I'm not going to spend much time going over this here. I just want to make sure that that you guys are comfortable with unit circle values. So I provided just some notes that I have from AB, and then for you guys to fill out unit circle just to make sure that you're being the degree measures is not as important. Just being able to get to the radian measures, being able to get that first quadrant ratio, and yeah. So I just want to give you just a practice handout, just so that you're very familiar and being able to review unit circles, so that if you see it on the quiz or test, that you're not wrestling with unit circle values. The other handout that I picked up, that I had you guys pick up, is this is just additional practice. These are test reviews from my AB class, but I'm not going to assign this for homework. It's just, if we have extra time between now and Thursday, for you guys to be able to have some additional work to use for practice. But really, it's this is the main one. Okay, so if you're able to, if you feel good about everything in here, then you'll just use the additional practice to kind of help supplement your just give you some additional practice problems. Okay, so I want us to just continue working through our test review worksheet. Hopefully we got through page 2 and we can start page 3. And then I'll walk through page 3 and 4 after a little bit. And then with our remaining time, we'll just work through the other additional worksheet that I have for you. Yeah, go ahead. As there's one thing that I left off of your test review. We'll make sure that we go over it today, but I want you guys to copy this down. Here we go. So this is number 25. I've got to put this on your sheet here. This is verifying IVT, intermediate value theorem. So just as a brief summary, intermediate value theorem says that as long as my function is continuous on the interval and both my endpoints are above, one endpoint is above and the other endpoint is below my target y value, then I know that my graph is going to cross that y value on that interval simply by these restricted information that we have. So continuous on closed interval, and then the endpoints, one below and one above. So let's go ahead and try this one first so I can make sure that you guys are good with this type of problem. These numbers are a little messy, potentially, but on the test, it'll be more manageable without a calculator. Okay. But for now, if you want to use a calculator, that's fine. Okay, so just wanted to walk through the problem here, make sure that you're comfortable with intermediate value theorem problems. So the first thing is we have to understand that we only need continuity on the interval. So we always do want to look for the denominator to see if there's any restrictions. And so here there is a restriction. There is a vertical asymptote at x equals 1, but it just doesn't interfere with the interval. Now, if your asymptote or break in the graph interferes with your interval, then you stop the problem and you say IVT doesn't apply. Okay. But in this case, we're safe because 1 is outside that interval from 2.5 to 4. So we can just state function is continuous on that closed interval. We're safe. And now we want to look for our endpoints, right? Our goal is to hit a y value of 6. So we need our endpoints to be one value below and one value above in terms of y value. These are x values. We got to insert these x values into the function and get their y values. So f of 5/2 gives us 35/6, which is around 5.8. That is slightly below 6. So we need f of 4 to be above 6. So f of 4, we do direct substitution into the function. We get 20/3, which is 6.7. So we're safe, right? We know we're going to reach a y value of 6 somewhere on that interval because I'm starting at 5.8 and I'm ending at 6.7. It's going to have to cross through and hit 6 because my graph is continuous for every point on that interval. So here is our justification. We can say by IVT, since 35/6 is less than 6, which is less than 20/3. Sorry, I forgot to put this here. I need to specify the location of that 35/6. So at 35/6 is coming from f of 5/2, and this is less than 6, which is less than 20/3, which is coming from f of 4. I know that f of 6 is going to have to exist for sure somewhere on that interval from 5/2 to 4, even though we don't see the graph and even though we're just basing this off of limited information. And then part B is saying find that C value. Okay, where is the location where the graph is equal to 6? So basically we just set the function equal to 6 and solve for x, right? We're just plugging in 6 in for the y and solving for x. So here I set my function equal to 6, I cross multiplied, I solve for x. Now, when I factor and solve for x, I'm getting two values, 3 and 2. However, we only care about the interval here. So even though the graph does hit a y value of 6 at 3 and 2, x equals 2 is outside the interval. So only 3, only when x equals 3 is what we care about for our C value, because our C value has to be inside the interval. So basically, this graph does hit a y value of 6 at the order pair of 3, 6. Okay, so you'll see one IVT problem on your test. The numbers will be easier to work with, so you're not having to struggle with those values without a calculator. I just want to make sure that you're clear on the conditions, you're clear on the steps, and that you know how to justify your answer. Any questions there? Okay, does anybody still need to look at this? Yeah, sure.
Like how, what are the steps to getting, like, that you know you're gonna be comparing the types of functions? Like, how do you get this versus, like,
What do you mean, number 6, which problem? This problem?
what's the beginning?
Oh, okay, this one here.
Like, how do you know you're gonna be comparing the functions instead of like the IV?
I think if we try to go through our comparisons, we're going to see it doesn't quite match, right? Because you can only compare degrees if you're dealing with a rational function,
Yeah.
right? So this doesn't fit in that category of comparing degrees. So our next option is, well, I have two families of functions, so maybe I can get that comparative growth rate to show up. Mhm. Okay, so I think I briefly talked about number 20 here. The mistake, or I forgot to add the types of discontinuity for number 20. But once we factor and reduce, we can see where the discontinuities are. Anything that cancels out is part of a whole, which is a removable discontinuity. Anything that's denominator that does not cancel out is part of a vertical asymptote, which is a non-removable discontinuity. And then 21, anytime we see a radical, we know that if the degrees are the same, that there's going to be split asymptotes on either side. We're still going to be finding the ratio, but just understand that there's going to be the ratio will be a positive version and a negative version. These degrees are the same because the square root of x to the sixth. Sorry if that x was missing here. Square root of x to the sixth, the same thing as x to the sixth raised to the 1/2, right? So if I have x to the sixth raised to the 1/2, that does equal to x cubed. So because the degrees are the same, we just take the ratio of the coefficients. Root 16 over 5 is just 4/5. But if we're going to negative infinity, any negative value, any negative large value that I plug in, I'm still going to get a positive. That x to the sixth will still protect any negatives that goes in to make it positive. And the denominator, however, will change signs. So that's why I have two horizontal asymptotes, one at 4/5 and one at negative 4/5. Okay, for 22, we have to make sure that we're looking at the appropriate piecewise function before we commit to evaluating the limit. So limit as x approaches infinity, we realize that we're talking about the graph that is extending to the left of the graph. That's x is less than 2. So we know we're working with that x plus 5 over 2x minus 4. And if we're approaching infinity, we know that we're comparing degrees. If we're comparing degrees, degrees are the same. So therefore, just the ratio of the coefficients. 2 from the left side of 2. So 2 from the left side of 2. We know that's referring to this function as well. This is the connected part of graph that is to the left of 2. So 2 from the left side of 2, x plus 5 over 2x minus 4. We always do direct substitution first. Direct substitution tells us that there's a vertical asymptote there. But we can't say it does not exist because it's only asking about that one-sided limit from, so it's either positive or negative infinity. So I insert 1.9. 1.9 will give me a positive over a negative, which is enough for me to conclude that this graph is going to be going down. Part C, 2 from the right of 2. So 2 from the right side of 2, that's in this region, right? If I think about values like 2.1, 2.2, those are all values that fall within 2 to 5. So I want to use 2x minus 5. But first things first, it's always direct substitution. We insert our whole number into the value, into my expression. If I get a real number, there's no need for me to do anything else, right? There's no need for me to do any decimals unless I realize there's a vertical asymptote. This is a continuous function here. So it's my direct substitution will take me directly to my limit. Part D, limit as x approaches 2. I think what the danger is that we may look at this and think that it's 12, but this is the ordered pair, right? For a limit, we have to look at the behavior on both sides of 2, and we have to rely on the x plus 5 over 2x minus 4 for the left side of limit and 2x minus 5 for the right-handed limit. Now, we have enough information gathered because we have the one-sided limits from both sides of 2 with B and C. And you can obviously tell that these are not approaching the same real number Y value. So that's enough for us to conclude that if these are not in agreement, my true limit does not exist at x equals 2. So that's why my limit does not exist, because my one-sided limits are not the same. Okay. Approaching 5 from the left. So imagine like 4.5, 4.6, 4.7. These are all values in this range between 2 and 5. So I'm just going to evaluate my whole number first. So 5, and for x, I get 5. Again, I don't do any decimals. The only time I do decimals in this case is just to make sure that I'm falling within the correct interval. But once I'm doing a limit expression, I'm always plugging in my whole number. I'm ignoring that one-sided limit. Okay, part F, approaching 5 from the right side of 5. That's referring to this last function here. So I'm going to put in limit as x approaches 5 from the right side of 5 for that negative x squared plus 4 over 5 minus x. First things first, direct substitution. We get something that tells us that there's a vertical asymptote. The limit does not exist, but it's a one-sided limit. So we're choosing between the infinities. So insert 5.1, and you're just testing the signs. Numerator is negative, denominator is negative. 2 negatives makes a positive. I know this graph is headed towards positive infinity as it gets closer towards that asymptote. Okay, part G, limit as x approaches 5. Again, we may be tempted to say 20, but 20 is the ordered pair. It's not the behavior of the graph around 5. We can rely, however, on E and F. E and F has one-sided limits. And again, we see that the one-sided limits are not in agreement. One side is going to 5, the other side is going to positive infinity. So we say that the limit does not exist. However, what if both of these were headed towards infinity? Okay. And what would your conclusion be here? Yeah, that's right. So you would say D and E, but then you would subcategorize it as positive infinity because both behaviors are consistent. So if you can subcategorize, I do want you to subcategorize. Okay, part H, limit as x approaches 3 from the right side of 3. We know 3 is safely between 2 and 5, so I'm just going to use that 2x minus 5. Again, just a clean substitution. That one-side limit doesn't do anything for us algebraically. We're just going to insert that 3. That 3 gives us that real number, so we stop. And then finally, approaching infinity. Approaching infinity, that is a value that's obviously greater than 5. So we're going to choose that negative x squared plus 4 over 5 minus x. We know that if we're doing infinity, we're comparing degrees. If I compare degrees, my numerator has a higher degree, which means that this is going to grow without bound, either towards positive or negative infinity. So I'm going to choose a large number like 100 for me to test to see which sign it will be. I'm getting a negative over negative, which is positive value, which is positive infinity. So I really like this right here because this really sees if we're understanding every one of our steps, right? Because sometimes we can get mixed up with, you know, when do I compare degrees? When do I plug in 100? When do I plug in a decimal? When do I just use a real number? So I think this is a really good exercise for us to see if we, because again, the hardest part is the first step, right? If you can nail down that first step, then everything else is going to be easy. But getting to that first step sometimes is hard because there's all these slightly different steps depending on what's presented to you. Okay, so any questions? Bottom of page 3. Okay, so this is the graph that I created. For your graph may look a little different, which is fine. I think our graph may look different around F, because if a limit doesn't exist, you have a couple of options. Okay, if the limit doesn't exist, you can make your graph a. Let me show you the options here. if a limit doesn't exist, you can make your graph an asymptote. You can make it an endpoint. You can make it two disconnected graphs headed towards two distinct y values. But if a limit doesn't exist, make sure you don't do this. Make sure you don't put a hole with the graph extending. This would indicate that the point doesn't exist, but the limit does exist. Okay, so just make sure if it says limit doesn't exist, and if I ask you to sketch a graph, you have various options, but make sure that you're choosing the appropriate option. Okay, you can do any one of these three, but that you don't accidentally, do something where the limit does exist. And if I'm approaching negative infinity is equal to a, this is indicating that there's a horizontal asymptote, but there's only a horizontal asymptote showing up on the left side. Okay, so the asymptote doesn't really apply for the right side because it's only indicating that asymptote for exiting the graph to the left of infinity, or to the left of my graph. And then part H, as I exit the graph, I want my graph to head down to negative infinity. So that's why I have that arrow exiting the graph going down. Okay, 24. Find the value of k, which makes the following piecewise function continuous. So again, anytime I see the word continuous, I know I'm just going to kind of follow through continuity conditions, and that will give me a nice structure for me to set up my problem. So I know my value in play is -2. So I'm just going to go through and find everything based off of -2. F of -2. So F of -2, I'm trying to find my point. My point comes from the first piecewise because of less than or equal to. So -2 goes in for X. I'm not able to get full resolution. All I can get is -4 plus K, but that's okay. I can keep moving and continue to gather information. Second condition, does the limit exist? Well, I have two different functions defined on either side of -2. So I got to do one-sided limit, once for the left and once approaching to -2 from the right. So I'm setting up my two one-sided limit expressions here, and I'm just going to evaluate them. Okay. So -2 in for X, I get -4 plus K. -2 in for K for my other expression, I get -2K plus -2K minus 3. Now I know that my function is continuous. So my function is continuous. I know that my one-sided limits have to be in agreement. Because they must be in agreement, I can set them equal to each other. And before I know it, I'm created an equation that allows me to solve for K. And I'm able to just find anything that I need simply just by going through my continuity conditions. Okay, so for the next 10 minutes, if you guys can finish this worksheet, and then if you're done with it, then start on the additional pages that I have for you. And you have the keys attached, but just work for another 10 minutes, and then we can stop at 5 minutes after 10. 5 minutes after. Let me know if you have any questions. I'll walk around and see if there's any questions I can answer. We will see that like that one behind, or if it's probably like that, I'll give you the factory, but hopefully expansion. And also, it's that kind of thing, it's just like pretty small. So, yeah, so it's an odd function with what's an absolute smell that the negative to so odd function is going to have that type X, if I can say, I'll say it. But there's massive scope there. These graph looks like this. That's just horizontal, it's M2 and M2. But then I got it.
Yeah. It's not. I would see because I'm studying gas.
Oh, you said, this is not.
Okay.
So there's only.